Okay, let's dive right in with this seriously mind-bending question. Could you realistically age 20 years while your friends age just 4 hours? Look, I know it sounds like pure Hollywood magic, but what happens when we strip away all that cinematic gloss and apply the rigorous, unforgiving laws of astrophysics? Well, in this explainer, we're going to break down the very real, very lethal, and honestly, utterly fascinating physics of time, gravity, and human survival.
We've got a great roadmap ahead. We're going to start with the reality of time dilation, then move into the extremes of black holes, explore the theoretical side of space-time, and wrap things up by speculating on future human evolution.
So let's kick things off with Section 1, Time Dilation Reality, and the observable science we actually have confirming it.
Right, so we know from Einstein's general relativity that time is in this absolute ticking clock perfectly synced in the background of the universe. It's actually warped by mass. And this isn't just some abstract mathematical quirk either. It has very real physical consequences. We've literally proven with atomic clocks on airplanes and GPS satellites that intense gravity stretches time. Meaning, if you're subjected to immense gravitational forces, your cellular degradation, your actual biological aging, genuinely slows down compared to an observer hanging out back on Earth.
But let's look at the cinematic extreme, right? The idea that 1 hour could equal 7 Earth years. For that math to actually check out in the real world, a planet would have to orbit a black hole that is spinning at 99.8% the speed of light. To do this without the planet instantly getting sucked in, it has to be what physicists call a Kerr black hole, one that rotates so incredibly fast it literally drags the fabric of space-time along with it. This allows for a stable orbit right on the absolute razor's edge of the event horizon. If you were standing on that surface, the time dilation would be so extreme you could theoretically hop back into your ship and return to a universe that is nearing its heat death.
But here is where we hit a massive gap between cinematic art and lethal reality. Filmmakers love to prioritize dramatic flair, giving us these beautiful, knee-deep, stable water planets. But the intense tidal forces required to get that specific level of time dilation, they would cause extreme tidal locking. The side of the planet facing the black hole gets pulled vastly harder than the far side. That creates massive internal friction, which would heat the planet up so much it would completely vaporize any liquid surface oceans. So yeah, no casual wading in the water.
Which brings us nicely to Section 2, Black Hole Extremes, where we pit cinematic art directly against lethal reality.
An absolutely crucial thing to understand here is tidal forces. Counterintuitively, they are actually inversely proportional to mass squared. What that means is, a human could theoretically cross the event horizon of a supermassive black hole without being immediately ripped apart. If you fell into a normal, stellar mass black hole, the gravity at your feet would be millions of times stronger than at your head. You'd be stretched into a literal string of atoms, a pretty gruesome fate physicists actually call spaghettification. But because a supermassive black hole is so unimaginably huge, its event horizon is pushed much further out. The gravitational gradient is way gentler. You could slip right past the point of no return and you wouldn't even feel it. Well, at first anyway.
Because while movies love to show a pristine, majestic plunge into the darkness, the scientific reality is totally different. You'd be slamming into an accretion disk of trapped gas, whipping around at near light speed. The radiation environment there, it's literally like sitting inside a nuclear reactor. Unless you have impossibly advanced protective gear specifically designed to prevent total molecular breakdown at the atomic level, the 100,000-degree gas and lethal gamma rays would completely fry an astronaut long before gravity ever became an issue.
And frankly, even if we completely ignore the black hole and just try flying to another star at 99% the speed of light, biology is still our biggest bottleneck. Space is actively trying to kill us. Prolonged relativistic travel brings harsh medical realities. It degrades our cardiovascular systems and causes severe muscle and bone atrophy. Not to mention these skyrocketing cancer risks from high radiation environments. But the real immediate lethal threat? Velocity. At near-light speeds, a microscopic speck of cosmic dust carries the kinetic energy of a bomb. Hitting just one of those would instantly turn an unprotected astronaut into plasma.
Okay, having covered the biological tool, let's scale things up to Section 3, Theoretical Space-Time, Wormholes, and the Wild Paradoxes they create.
To bypass our current limitations and the universal speed limit of light, we'd have to look at folding space itself through a higher dimension. But here's the catch. Gravity naturally wants to crush an Einstein-Rosen bridge, a wormhole, shut instantly. To keep the throat of that wormhole open, you need a purely hypothetical substance with negative mass called exotic matter. It pushes space-time outward. Now, while this is mathematically possible using advanced quantum physics tools like the Casimir effect or quantum tunneling, the sheer energy scale required to safely pass a human spacecraft through is, for now, completely beyond our wildest capabilities.
The best way to visualize this is through a really brilliant analogy. Imagine our three-dimensional existence is like being swept down a raging river of linear time. We're just tumbling forward in the current. But if you could somehow access a higher spatial dimension, often called the bulk, you could essentially step out of the water and onto the riverbank. From up there, time isn't a flowing current anymore, it's a physical landscape. You could look upstream at the past, downstream at the future, and experience a totally nonlinear reality.
Now, you might be wondering, doesn't that break the rules? Well, general relativity equations actually do permit things called closed time-like curves, which mathematically allow for backward time travel and bootstrap paradoxes, but quantum mechanics kind of acts as the universe's cosmic traffic cop here. Physicists came up with the chronology protection conjecture. The basic idea is that quantum fluctuations would rapidly build up and instantly destroy any time machine before you could even use it, stepping in to protect causality and prevent universe-breaking events like the grandfather paradox. So who could actually safely harness these immense cosmic forces? That brings us to our final section, future human evolution and the Kardashev scale.
To even think about manipulating gravity or constructing stable wormholes using what physicists call Planck energy, humanity would have to undergo an immense evolution. Let's put this in perspective. Right now, we aren't even a Type 1 civilization. We're hovering around a 0.72. To stitch together higher dimensions or survive the lethal radiation of an event horizon, you don't just need the energy of a single planet or a host star. You would literally need to harvest the raw energy output of an entire galaxy, evolving into a full-blown Type 3 civilization.
And this leads to a truly fascinating speculation, a kind of ultimate bootstrap paradox. What if the mysterious entities manipulating wormholes in our science fiction aren't aliens at all, but simply our own heavily evolved distant descendants? Just imagine a Type 3 human civilization, millions of years from now. They might have biologically adapted to survive extreme high-gravity environments, mastered quantum mechanics, and now exist as bulk beings in 5 dimensions. They could be reaching back through a closed time-like curve to engineer tools like tesseracts, ensuring their own survival in the distant past.
It really leaves us to wonder, is mastering the extreme physics of time dilation and gravity our ultimate evolutionary destiny? You know, when ancient cultures looked up at rare astronomical events, they often wrote texts interpreting them as divine phenomena, or transcendent beings coming from the sky. Today, we watch movies about 5D entities saving humanity. But what if, in both cases, we're just looking into a mirror, reflecting millions of years into our own future? If time is truly a landscape waiting to be navigated, maybe our destiny is to become the architects of time itself. It's a lot to wrap your head around for sure. Keep looking up and keep asking questions.